Alrighty, y'all. Today we're taking a look at the recitation for March 4th. And this one we're going to be looking at some orbits and our Newton's law of gravitation right over there. Right. So for our first question, right, we're trying to find the altitude of an orbit so that it stays in a fixed position relative to Earth. Right. So the orbit's synchronized with Earth's rotation. Right. So we're going to start. Our sum of all forces on the satellite. I actually draw a force diagram first. Right, so here's our Earth. Right, let's draw our picture of what's going on. Here's our orbit going around the Earth. And here's our satellite, right? What a cool looking satellite. It looks like a fly, but it's flat. Right? So at that point in the orbit, or at any point in the orbit, right? Gravity is just going to be facing towards the Earth, right? So I'm just going to be drawing that, like at the top, like where it is, where I drew right there, our force diagram just looks something like that, right? Just our gravity. Cool. So now if we do a quick sum of the forces in that y direction, all we have, and I'm going to say down is positive just for our purposes. So all we have is that Fg, right? And that equals our mass times our acceleration. Cool. Wonderful. So now we have to figure out some more of the pieces, right? So we know we're going in a circle around the Earth. So our acceleration, right, the acceleration of something that goes in a circle is just going to be our omega squared times our radius. Right? Cool. What is our omega for this, right? I have to figure out how fast around the Earth it's traveling. Well, if it's lined up with Earth's rotation, so it's going at the same angular velocity as Earth travels 2 pi radians, right, a full rotation, for every 1 day, right? Every day it goes around once. So we can convert that, right? 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. Ooh, and that's going to be approximately like pi over that. And that's in radians per second. Right? There's our omega. There's our angular velocity. That's how fast we're going around in the circle. Now what's our radius, right? Right, so our radius is going to be our distance to the center of the circle. So however long this is. But we don't really care about the radius right off the bat. Right? We're trying to solve for the altitude of the orbit. Right? We're trying to solve for our distance between the surface of the Earth and the satellite, right? So I'm going to call that h for like a height, right? And our radius of this circle, of our circular orbit, is going to be whatever the radius of Earth is, plus that h, right? So now I just get to say that r is going to be, I'm going to use big R for our radius of Earth, plus h, right? And we're trying to solve for h, right? So we have our acceleration, right? We're thinking of a mass as a property of our satellite. We're not going to bother with that just yet. All right, let's look at our Fg. Right, so using our Newton's gravitational law, right, we have our g, big M, little m over r squared. Again, our radius, right, it's our distance from our thing to the center of mass of our other thing. So it's going to be the same, r plus h. I should say Fg equals, right? So as I'm doing this, right, our big R plus h, we square them both, right? We can't just distribute the squared in, right? I gotta FOIL it all out. Our g, that's a universal gravitational constant, so that's just gonna stay, right? And our m, our big M, well, it doesn't matter which m is which, but right, I'm gonna say the little m is the same mass as our satellite. And our big M, that's gonna be the mass of the Earth, right? So we just leave all that the same. But now if I plug this into my equation up here, and I plug this in as well, right? Plug in for Fg, we have g, big M, little m, mass of the Earth times the mass of the satellite, over r plus h, all squared, equals, right, mass times our acceleration, which we said was pi times whatever that is, 43200 omega squared. And we said that was times our r, which was our radius of the Earth, plus h. Okay. Radius of the Earth, cool. Simplified equation. Mass of the satellite and mass of the satellite are going to cancel on out. I'm going to move this, multiply both sides by it to get it out of the fraction. So we're going to have g, mass of the Earth, equals, right, squared here, 1 here, so it's going to be, we have our omega squared, and then it's going to be our r plus h cubed, right? And remember, we're solving for this h in terms of everything else, right? So I'm going to try to isolate h. Right? So if I divide both sides by that, I get g m over pi over 43200 squared, right? And that's going to equal r plus h cubed. Now we raise both sides to the 1/3 or take the cube root, whatever you prefer. They're the same thing. Pi over 43200 squared, all raised to the 1/3 equals r plus h. Now, since we're solving for h, we're just going to subtract r from both sides. I'm not going to rewrite it again. I'm just going to subtract r from both sides. And that's going to equal h. Right? So now we have everything. We have an expression for h in terms of things that we hypothetically know. Like obviously we know pi, and that makes our omega. But now we have our universal gravitational constant, right, which is 6.67 times 10 to the negative 11, right? We have our radius of Earth, right? And since we're keeping everything, we're using everything in kilograms and meters, right? Make sure we have it in meters, right? So our radius of the Earth is going to be roughly 6.371 times 10 to the 6th meters, right? And then our mass of the Earth, that's going to be roughly 5.972 times 10 to the 24th kilograms. Right. Cool. Plugging all that mess in, right? Plugging all this in, punching it into a calculator, it's going to give us an h, or an altitude, of roughly 3.58606251 times 10 to the 7th meters, right? Or, rounding for sig figs, 2.59 times 10 to the 7th meters, right? So that's how high above the surface of the Earth we would have to orbit for gravity to hold us in our circular motion. Cool. Question 2. Now we're talking about apparent weight. And look, they gave us all those things that I just gave us before, right? Length of 1 day, right? This is our 2 pi over our however long a day is in seconds, right? So now, right, Newton's universal law of gravitation, we're going to determine the force of gravity on a 1 kilogram mass resting on the surface of the Earth, right? So we are going to start punching some stuff in, right? So our force due to gravity, right? Our big G, right? Which is our 6.67 times 10 to the negative 11. You can go to more decimals, but that's how far I have it memorized, so that's how far we're going to use it, right? And then our big M for this one, again, it doesn't matter which M you call which. I just use big M as the bigger thing, right? So our big M, that's the mass of the Earth, which is, again, 5.9722 times 10 to the 24th. Again, we're keeping everything in, like, kilograms and stuff, right? And then our little m is our 1 kilogram. And then we divide by our radius squared, 6.371 times 10 to the 6th, right? And that's all squared. So punching that into a calculator, right, is going to give us roughly 9.820008021 newtons. right? Since we kept it in kilograms and meters and all this stuff, right? Final answer in newtons, right? Which kind of makes sense. 9.82, that's pretty close to what we're, like what we expect, right? We've been using 9.8 or like sometimes 9.81 if you're really just feeling spicy about it, right? So that's just the force of gravity of something resting on the Earth, right? And now we're looking at the scale on the North Pole, right? Sitting with Santa Claus. Okay, so scale at the North Pole with Santa Claus. Okay, so now the scale measures the normal force that's being exerted, right? What would the scale read, right? So if we think about it, right, this is just using the gravitational law, but a thing on Earth, we were saying that our satellite's spinning at the same rate that Earth is, which makes sense, but that means that something on the surface of Earth staying the same position is also going to be spinning, meaning that sum of our forces isn't just going to be zero, right? Except at the North Pole, right? Because we say the Earth spins around an axis and someone's standing here, right? If it's spinning around kind of this way, it's kind of hard to see. There's a lot of arrows and stuff going on here. But if we're spinning around this axis like this, whoever's standing up top here isn't going to be having any kind of circular motion, right? So our circular motion, right, we're not going to have circular motion for this part. So for this part, our sum of our forces is actually zero, right? So for this one, we can say sum of the forces is zero. So our normal force, right, our person standing here has a normal force acting up and an FG acting down, right? We can say that our normal force is going to be equal to this because we have to say that our normal force acting up minus our gravity acting down has to equal zero, right? So we're going to say their magnitudes are equal, right? Since our sum of our forces has to be zero because we're not accelerating, because we're not going in a circle, right? So there's no, like, we're not rotating at the top, at the North Pole, so we just ignore that, right? So for this case, we conclude the value of G is just our GM over R squared, right? So I take that and multiply by M. I say this is equal to G. Or really, if I write it backwards, mg, that's just our normal that we've been using for gravity. Right. But now, right, we're going a 1 kilogram mass resting on a scale sitting on the equator, right, somewhere in Kenya. Now we have to think about what this scale would read. So this is where we say, right, our sum of all forces, right, now since we're rotating around our equator, our sum of our forces isn't going to be zero because we're going to have some acceleration, right? So our sum of our forces isn't going to be zero. So we have to say that our sum of our forces is going to equal our mass times our acceleration. Since we're going in a circle, that's going to be our omega squared r, right? So now we figure out our sum of our forces, right? So we have a person standing, right? There's our gravity. Here's our normal force, right? And this is a person standing on the planet like this. Ooh, if it works, right? So this is if I'm looking down, here's the North Pole. I'm looking down at the Earth, so the person's spinning around like that, right? The Earth's not perfectly circular or spherical, but we're going to pretend for right now, right? So now we say that our sum of our forces is our normal force. Actually, I'm going to say that our acceleration, since I'm saying our acceleration is going to be positive, down is going to be positive, or towards the center is going to be positive. So Fg minus Fn equals m omega squared r, right? And again, this is just the radius of Earth now. Since we're not at an altitude, we're just the radius of Earth, right? So solving all of this out, right? We plug in our gravitational constant, our gravitational law of gravitation, whatever, you get it, m over r squared, and minus m omega squared r equals r Fn. Okay. So now if I factor out the m times r g m over r squared minus omega squared r, right? If we plug in, right, again, if we plug in our mass of our Earth, our gravitational constant, the radius of the Earth, and that same omega that we were looking at before, right, this one would give us roughly an acceleration, or if we assumed that the mass, again, was a 1 kilogram object, right, 1 kilogram object, plug it in, we get that our force, plug all that in, all right, it's going to be roughly 9.79. Right? So still rounding to 9.8, but very different from our 9.82, right? So what we now do, since we factored out this m, if we're saying that this is our force from gravity, and we say that our gravity is equal to mg, right? Now this becomes our g at this point, right? So now we have to look at, right, so our apparent weight is going to depend on the location on Earth. So we have to define g as either our Fg divided by mass, right? If we say that Fg equals mg, right? If we're defining g divided by mass, that's how we're defining g. Or if we do it with our Fn over the mass, right? Because if I do a normal sum of all forces and assume the acceleration is 0, our normal force minus our Fg has to equal 0, right? So we get that Fg is our Fn. So we can define g, in this case, as Fn over m, right? But we can measure our normal force. We can't necessarily measure this at any given point. We can calculate it and kind of try to figure it out. It's harder to measure that. We could, but, right? So really, what we were talking about, if we're just adjusted for the centripetal stuff, this value for g, our Fn over m, is going to give us a more useful value. Because in reality, we don't really care what the gravity force is. We care about like the net effect. And if we use an altered value of g, then we can say that approximately our Fn equals our Fg and our acceleration equals 0, right? If we're just saying that our g changes, then that's going to give us a more useful value that requires less math, right? It can be useful, it can be measured, and this, right, the normal force is the one that really is going to be like affecting other things. Like when we start getting to friction, right, our normal force is very important, right? So the fact that we just have an adaptable g means that we'll have a more accurate reading for our normal force, which means we'll get a more accurate calculation for our friction forces and stuff, right? So now, is the distinction likely to be relevant in engineering? Yes, absolutely, for me specifically. It depends on your engineering. I'm in aerospace engineering, clearly launching some rockets at high altitudes. I'm going to be doing a lot of orbital mechanics just like this, right? So this gravitational law, having a distinction, is probably going to be pretty important. However, if we're like building stuff on the Earth, it's probably not as important because, right, you have that safety factor, you have a safety factor built in. So it doesn't matter if you're off by just a little bit because you made it 10 times more safe than you would need it to, and it's not going to collapse under its own weight. It just depends on the level of precision that you're going for. Right? Because if you're just estimating, if I'm estimating everything to my 2 sig figs, right? 9.79 and 9.82, both round to 9.8. So if I'm okay using the 2 sig figs, then it all works out and I'm all set, because they'll just all round to the same value. But it does, if you try to get more precise than that, right, you might want to be a little bit more accurate, right? All right, so the astronaut's in orbit, right? Moving on, right? We're not so far away that it doesn't feel like gravity, because we're still pretty close. Remember what we were talking about up here. In orbit, we're still feeling a force from gravity, right? So why does the astronaut feel weightless, right? It's kind of like what we were talking about with, like when we had the frog in the bucket, right? The reason the frog doesn't fall out of the bucket is because the bucket is moving at the same acceleration as the frog, so they're not moving relative to each other, right? It's the same thing where the satellite, the like International Space Station is moving at the same acceleration as the astronaut. It's because it'll at this point, right? If we say we're solving for our acceleration, ma is going to be our gravity, at whatever altitude we're at. That's going to be independent of our mass, which is really the only thing differentiating our spaceship and our person, right? Because they're both the same distance away from the surface. So they're going to have the same acceleration. They're both accelerating towards the center. So they're not going to be accelerating relative to each other, right? They're going to have the same magnitude, and it's going to be the same direction because, right, they're both going around the Earth. So it's always going to be pointed towards the center of our circle, which is towards the center of Earth. Okay? Now we draw a force diagram floating in the space station, not touching any of the walls, right? The only thing, if we're not touching anything else, the only thing acting on our astronaut is this gravity. Right? And we said the astronaut doesn't seem to fall, but really the astronaut is falling. The astronaut is accelerating just from gravity, but the acceleration is changing as we go. The direction's changing, so we're just going around in a circle. It gives us this circular motion. And now we ask, is the astronaut truly weightless? What does weightless mean, right? So is the astronaut weightless? We can define weight in a couple of ways, right? We were talking about our apparent weight before, right? Our normal force, right, as our apparent weight, right? And if we say that this is our definition of weight, are we weightless? Well, yeah, we don't have a normal force, right? That's how heavy the person feels. They feel like they don't have any weight because there's no normal force. But if we define our weight as our force from gravity, right, then no, we're not going to be weightless because, right, gravity's still acting on us. There's still a force exerted by gravity on our astronaut, right? So if it's this, then we're weightless. But if it's this, then we're not weightless, right? Because our weight will still exist at this point. It just won't look like it'll have an effect relative, right? So really, the thing is, our weight is our force from gravity. That's what I'm going to say. That's the answer that I'm picking. That's what I'm deciding on. That's how I'm just going to refer to it from here on out. Meaning that in orbit, our astronaut is not going to be weightless because we still have a force from gravity, right? But we don't have a normal force because we're still accelerating, so we don't need anything to cancel that out. All right. Well, I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this recitation or any other problems that you want me to try to explain, and I'll do my best to try to explain them because I guess Sydney explains stuff.